This is a video for using a prism for modeling for exponential and logarithmic functions. So what we're talking about is if you happen to notice a pattern that is following in a scatter plot an exponential function. So not just a linear pattern as we've seen before. You might see a few dots and they're going fairly in a straight line like you did in Algebra 1, we did earlier this year. But we can clearly see it's growing exponentially or even growing logarithmically. If we have a situation like this, we're going to be using a different type of model. Now we're going to do this on the prism. However, if you don't have your prism or something's wrong with it, I am going to post on Google Classroom post websites you can use that are similar to the prism to get your regression equations. Okay, so we're going to start with the points in the prism. We're going to be tracking trampoline store values, years 1 through 7, and the number of trampolines sold. And you can see it's growing, getting pretty big, up to 50, and it's really exploding as a store. And I have those values in list 1 and list 2. So the years are in list 1, and I put in 1 through 7. List 2, the number of trampolines sold. Okay, so we're going to walk through it first. Let's take a look at the steps. So if you want to pause and write those steps down, we're going to go F2, calculator, and we're going to calculate regression. And I don't want X, I don't want linear. I don't want any of these that we used in other chapters. We're going to go F6, EXP for exponential. And you can do a base E1. We're going to stick with AB to the X. So I'm going to click AB to the X, and I can see. Now remember, A is the number in front. That's your Y-intercept. B is the base number. That's the key number. So what I have is 8.457 for the A value, 1.4188 for the B value. R is pretty strong, so my correlation is pretty good. And so we're going to come down here, we're going to write our equation. Y equals 8.457 times, and I like to use parentheses, and again, this is exponential, so I'm raising it to the x power. It's not times x, it's being raised to the x. I'm going to put my b value in here, 1.41, we'll go 88, take it out a little further. And that's the equation that predicts the number of trampolines being sold. A couple of keys of note to tie into the last chapters. Take a look at this b value. We know that b is 1 plus the rate, so we can infer what the rate is. The growth rate of his sales of trampolines is a 41.88% or almost 42% increase. So he's increasing his sales almost 42% year after year. This is the starting value. So if we were to track this back to the beginning of his sales before we started tracking it, almost like the 0 year, to infer the 0 year, number of trampolines being sold was 8.5. And we're going to use that equation then to make a prediction. So here's represents the trampoline store sales, and we're going to predict the sales in year 8. So I'm going to take this function, I'm going to put 8 in for x. A couple things we can do. You can just go into Run Matrix, type that equation in, and make your prediction. But we did talk earlier this year about how to copy. Press execute. Again, press copy, and then you have to press execute. Then when I go into my table app 7, I can press F1 to turn it on. And then when I go into the table, if I type in 8, it'll give me my prediction, 138.9. So I predict that approximately 139 trampolines will be sold in year 8 is what they would anticipate. And again, it's growing exponentially, so it's growing really, really, really large. How do I know that this is exponential? Now, most of the time I will tell you. One other thing you can do is in once you put your data in, you can press F1 for graph, F1, and you can see it's starting to grow exponentially. You can see it turning, that turning point here where it's starting to grow really, really, really steep, and over here starting to approach the asymptote. Next, we're going to do one for a logarithm. So I have an example from a book here, talking about the logarithmic pattern that measures atmospheric pressure that decreases as you increase in altitude. So as you're going up, and they have an example here like a weather balloon, or whether you're climbing a mountain, whatever it is, we're going up. At sea level, the average air pressure is 1 atmosphere, and they have another number here in kilograms per square centimeter. The table shows that pressure P in atmospheres. So P is the number of atmospheres at certain altitudes H. So it's the height above sea level. We're going to use a graphing calculator to make a model. And when we make these models, we're going to do them all in ln as a natural log, because it's the one that occurs most naturally and most often in nature. And then we're going to estimate the altitude with a pressure of 0.75. So again, here's my air pressures. At sea level, altitude of 0, the air pressure is 1. As the air pressure decreases, as x approaches 0, and we know that a logarithmic function goes something like this. So as the x value is getting closer and closer to 0, what's happening to the y value? Well, you can see the y value keeps going up, 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 up. That tells me that this is going to be one that's flipped around, that as it gets closer to 0, it's going up, 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 up. So it's a logarithm that's been reflected around the x-axis and transformed in some way. Okay, so again, here's my air pressures. And you can see as the altitude goes up, the air pressure is getting much smaller. And so we're going to put this in the graphing calculator, and we should come up with something that looks like this. The A value, the B value out in front of ln. Okay, so let's run through that on the calculator real quick. And again, I'm going to put a link on the Google Classroom post. So if you don't have a graphing calculator, it will have a link for a logarithmic and an exponential calculator. You could do a search and find your own also if you want to. So I'm going to go ahead and put those values in. 1.55, these are my x values, the air pressure, 0.12, 0.06, 0.02. Let me get rid of that last one. Now let's pop up here, and we're going to go 0, 5, 10, 15, 20, 25. And we're going to do the same thing as before. We're going to calculate regression. And when I go F6, there's my exponential I was using. There's a log right there. So if I press log, you'll see it comes out in the right form. A plus B. Let's talk about that real quick. Y equals A plus B ln x. So B is a vertical stretch because we're multiplying ln. A is a movement up or down. Normally, a lot of times we'd see it over here. They're putting it out in front, so it tells me how much it moves up and down and how far this has been shifted up. And again, I expect B to be negative because of the shape of the values. So what I find is A is 0.8626, we'll round that to 3, and B is minus or negative 6.447 times the ln and x. So A plus B times ln x. So it's going to look like this. Y equals A plus B, and it's a negative B value, times ln x. And that predicts the altitude. Now, we're going to put this into context. So P is my x value. So I'm going to change this to BP. And Y is the altitude. So it's going to be H equals, to put it in context, that minus that times ln P. Now it also asks us to make a prediction for when the air pressure is going to be 0.75 and that atmospheres, and that is P. That's going to be the x value. So again, I can click copy and copy it in there, or we can just go to the menu. Let's do it in run matrix this time, and I'm going to type in 0.863. minus 6.447 times the natural log of P, and I'm going to predict that for 0.75. And what I get is a height of 2.71. Let's go 7. We'll go 4 decimal places. Okay, and that's in kilometers was our units, I believe, height in kilometers. And so once you get 2.7 kilometers above sea level, 2.7177, that's when you have atmospheric pressure of 0.75 atmospheres. Make sure you get online in the Google Classroom and take a look at the assignment posted there.